Now let's move on to another example, and this example is essentially doing image compression using SVD. Okay, so what we want to do is we want to, take an image and use that image and do an image compression of the image. So the image that you see here is an image of a car, and we will use that as an image and you run this whole example or next set of code blocks using the example that we have. So if you look into this, first thing that we will do is we will import this image and we will convert that into a gray scale. And since I'm using Google Colab, if you have to import, right, what you can do is you can click on the folder, okay, and then you can click on this icon here, and you can do the choose file, and you can essentially go to your your drive where you're locating or where you have placed the images and so on, and from there you can upload images, CSV files or TXT files that are there, and that could be used to essentially upload different things that you want to use in your code blocks. So again I will this is how I essentially I'm going to import. That's where the location of this car image is going to be, and that's how I'm going to import that and use that in my code block. So this source code block, what it does is essentially reads the image, okay, and then essentially it also converts this image from a color image to a gray image. So the code block that you see here, what it's doing, it's basically taking and converting that colored image into gray, and we are doing this for simplification purposes and so on. So this will simplify the overall thing, and then after conversion of the gray image, we are essentially doing the SVD computation for this gray image itself. So similar to the previous code block, what we are doing is we are essentially calling .svd function that is there in the numpy, and we are passing on the gray image, and this gray image is essentially representing the overall car image in a grayscale in a matrix form, okay. And once we do that, we are able to get this three different matrices, which is U, S and V, which are representing the singular value decomposition of the gray image matrix representation. And so let's go ahead and implement this code block and see what this decomposition looks like. So after I run this code block, you can see that the shape of U matrix is 183 comma 183, and the number of singular values that is there, the shape of S is 183, and also the shape of V is 183 times comma 275. So from above, what shape you can say that the matrix generated from the image has essentially 183 linearly independent eigenvectors, right? But this is a lot of dimension, and probably all of that dimension is not going to be useful in representing the image. So the question is, can we compress that image and can we represent this image in a slightly lower number of dimensions. So that is what we are going to be doing, and in order to do that, what we are going to be doing is we will be using this metric of identifying the variance of the image using singular vectors. So we will see how much each of the singular values or singular vectors are contributing to the variance, and based upon that we will pick few of the important ones and use that as a basis to do the image compression that we have, okay. So in this code block that you see here, what we are doing is we are essentially importing Seaborn, which is essentially a statistical data visualization library in Python, because we want to compute the variance contributed by each of the singular vectors that is out there, and we will print out essentially the variance explained by the top 20 singular values. So this code block essentially helps us in essentially printing out what is the contribution of each of the singular values in the overall thing. So if you run this, it essentially will plot, give a plot, and as you can see from this plot, that probably the first singular vector is the most important one, and it is essentially capturing almost all of the information, and it turns out that the first singular value and the singular vector is able to explain the 96% variance in the overall data, okay. Now as we move on to the second and so on, the contribution of those singular values are diminishing and they are smaller compared to the first different. But as you will see that even though if the whole most of the explanation is done by the first vector, we will need a little bit more than just a one singular values to represent and do the image compression, right? So let's move on and see how just few eigenvectors could be used to do reconstruction. So what we are doing here is we are taking, you know, different size of singular values and singular vectors and varying them from size of 1, 5, 10, 15 and 20, and we are doing the image reconstruction based upon that and comparing that with the original full 118 dimensional reconstruction space. So if I run this code block is essentially, reconstructing the image with different number of singular values and singular values. So the plot that you see here essentially represents, the reconstruction that has been enabled by using n components, and the n component essentially represents the number of singular values that we are using for reconstructing. Now, even though you see, one of the important things that you can see is that in this image on top left, you essentially have, the full image, which is 180 dimensional linearly independent vector that is there. In the top middle, you have the reconstruction that has been enabled by the first most important singular vector, which captures the 96% variance. And then we move to top right and we see how the image has been reconstructed when we use 5 singular values and 5 singular vectors. And then progressively in the bottom row, when we move and increase the number of singular values and singular vectors to 10, 15 and 20 and so on, right? So if you look into this, right, even though the first component is able to capture 96% of the information, qualitatively it is not reconstructing that image very, very clearly. Okay, so even though it's the most important one, but just using one dimension might not be good for qualitatively very close reconstruction to the original image that might we have. As we are increasing the number of components or number of singular values and singular vectors that are used for compressing and reconstruction purposes, you can see when the n component is going and increasing from 1 to 5 to 10 to 15 and 20, the clarity of reconstruction is increasing. In fact, it turns out when you have using the first 20, when n component is 20, that image is a very, very fairly good approximation of the actual image that you have. So, you can say from this qualitative results that maybe when you use the first 20 singular values and the first 20 singular vectors, then using that you will be able to do the image compression. The quality of that image compression is going to be very, very good.